All right, we've already talked about the work energy theorem and that the net work results in a change in kinetic energy. And I like to call kinetic energy energy by virtue of the motion of an object. And we wrote that K was equal to 1/2 times the mass times the speed squared. Well, there's another type of energy we want to introduce called potential energy, and that's the energy by virtue of the object's position. And we normally use the symbol of U for this. And what I'm trying to do in this video is figure out what should the expression be for the potential energy due to gravity. So what I'm going to do is just a little thought experiment here. I'm going to have a little mass of M, and I'm going to raise it up a little bit higher. And hopefully right from the beginning you agree that I've just increased the potential energy. So I'm going to go ahead and put in my displacement vector here, just so I don't forget which way the process was going. And I'm going to call my initial y value y initial, and my final y value y final. And what I'm trying to do here is find the work done by gravity. So it's a little bit hard to convince yourself to stop thinking about how you would have to push on this thing to get it from here to here. You'd have to push up. But what I'm trying to find is the work done by gravity, not the work done by you. So gravity, force of gravity is going to have a magnitude of mg and point down through this entire process. And if I try to get the work done by gravity, well, it's got to come out negative because the force vector points exactly opposite to the displacement vector. So I'm just going to put a minus sign on there. And then the magnitude of the force is mg. And then I need the size, the magnitude of the displacement vector. Well, this y value is bigger than this one. So to make a positive quantity come out, I've got to go y final minus y initial. And there's the work done by gravity. So I could distribute that mg, and I get an mg y final minus an mg y initial. And here's where we give this thing a new name. And we're going to call it gravitational potential energy. All right, so mg times the y coordinate, mgy, is going to be called gravitational potential energy. Now, I can rework this expression for the work done by gravity. And the reason we kept a minus sign out in front is because we're looking for a delta, and a delta is always a final minus initial. So mgy final, that's the final gravitational potential energy. Mgy initial, it's the initial gravitational energy. And so I arrive at this somewhat disturbing expression. The minus sign always feels a little bit hard to comprehend. That the work done by the force of gravity is the negative of the change in the gravitational potential energy. So what I like to do is immediately follow up with a thought experiment where we're going down. So the mass is going down from here to here. And I want to look at the work done by gravity, so I'm going to go on the way down. The work done by gravity will be the negative of the change in the potential energy. So that'd be the negative of final potential energy minus initial. So the final now would be mg yi. It's a little weird to call the initial y coordinate the final, but we are on the way down, so that's the last y coordinate. My initial was y final. Again, because we're starting here and finishing here for this little thought experiment. So when I look at these y coordinates, well, y final is a bigger number than y initial, which makes the interior of this negative. With the minus sign out in front, I get something that's bigger than 0. So I can tell that this system is working. Gravity does positive work on the way down. And that's when you would see that gravitational potential energy converted into kinetic energy.